Thank you so much for the invitation. It's always a delight and I'm thrilled to be at UConn. It's been too long. Now that I'm in Boston, I'm closer. I got to get here more often. So I really appreciate the opportunity. This is an interesting project. A while back, I had been working on conditionals, triviality results, and I'll be talking about that kind of stuff today. And so I did a bunch of work on that. And this, in a sense, is a follow-on to that, but in a kind of a weird way. Recently, I don't know for what reason, I'm not really sure how it happened, but I was reading David Lewis, I think it was over winter break, and I was reading just a series of Lewis papers. And I noticed that there was an inconsistency in Lewis. And that's what inspired this paper. Okay, so let me give you a little overview. So it turns out that Lewis articulates two incompatible conceptions of what it takes for a constraint on degrees of belief to be a rational requirement. So in 1976, he wrote a very famous paper about conditionals called Probabilities of Conditionals and Conditional Probabilities. In that paper, he articulates a notion of rational requirement for degrees of belief, which is very strong. And I'll explain just how strong it is. And he there assumes that all rational requirements have to hold in a what I'll call a resilient way. And I'll tell you what resilience is. That's a precise concept. I'll get to that. And that requirement of resiliency turns out to lead to trivialities. And I'll talk about those famous trivialities. 4 years later, he wrote a paper about objective chance and its relation to degrees of belief called A Subjectivist Guide to Objective Chance. And in that paper, he articulates a different, more permissive conception of what it takes for a constraint on degrees of belief to be a rational requirement. And there he explicitly denies the requirement of what I'm calling full resiliency. He identifies what he calls inadmissible exceptions to resiliency. And by doing that, he avoids certain trivialities for the relation between chance and credence. So when I was reading this recently, it dawned on me, well, which conception is the right one? If you look at the literature, and there's a vast literature on conditionals that can't stem from that 76 paper. And if you read that literature, you get the sense that it led many people to reject this constraint that I'm going to call the equation, sometimes called Adams' thesis or Stalnaker's thesis. And then the 1980 paper actually led many people to accept another constraint called the principal, which is about the relation between chance and credence. So that's weird. I'm going to get into the details of just how weird it is. It's actually extremely puzzling what's going on in these two papers. So here's what I'm going to do. I'm going to take the more permissive notion, the notion from the 1980 paper, and I'm going to explain how, if you look back at the literature on Adams and Stalnaker, the literature on indicative conditionals and credences, through that lens, you can articulate a completely triviality-free way of understanding those constraints. Not only that, but it appears, and now I've also been looking into the empirical evidence, talking to linguists and stuff, it appears that what you get by doing this is actually a rational requirement for credence. Okay, so one way to think about this is this. When Lewis wrote the 76 paper, because he adopted this very strong conception of what it takes to be a rational requirement, he was being, in a sense, uncharitable to Adams, to Ernie Adams, and Bob Stalnaker. Then later, when he renounced that, he never went back and revisited his reconstruction of those Stalnakerian and Adamsian arguments. But if he had, he would have discovered that there's a perfectly good rational requirement there to be articulated. So that's what I'm going to tell you about. Okay, so I'm going to start by talking about Lewis's 76 paper, what's going on there, and how it's really very strong assumptions about rationality. Then I'll switch gears and talk about the 1980 paper, and then I'll say, okay, well, let's take the more permissive notion of rationality that occurs in the 80 paper, because I actually think that's the correct one for reasons that aren't just dependent on conditionals. And then I'll just show you how to do it. There's a way to do it that works and appears to be correct. Okay, so we're going to be working with some very simple models. Okay, so I just want you to imagine a simple Boolean sentential language, a truth functional language, with two atomic sentences, P and Q. So it would help maybe if I wrote something here. So we're doing a very simple family of models where we're going to have an atomic sentence P and an atomic sentence Q, and these are factual propositions. This is important because Adams was only talking about factual claims. So there's no modals, there's no conditionals in these things. Okay? These are factual claims. And then what I want you to do is think of a third atomic sentence, which I'm just going to name P arrow Q, but that's just a name. It's important that that's not a relation between P and Q. It's just another atomic sentence, which I'm going to extra systematically interpret as the indicative conditional connecting P and Q. Okay. So we're just going to start with this simple case where we have an atomic sentence P, atomic sentence Q. They're factual, and then I'm going to introduce a new atomic sentence, which I want you to interpret in your mind, but not systematically in the model, as the indicative of P and Q. And so this is, of course, going to set up a space with 8, if you will, state descriptions or possible worlds in the usual way. I'll be showing diagrams of this later, but just to give you a sense, this is the usual. So this is the kind of models I'm going to be talking about, and at first I'm just going to talk about a single model with a single P, Q, and a single conditional, but we'll extend it later to arbitrary pairs of factual claims. Okay, so now with this model in mind, and we're going to and we have a probability function over this. So probabilities, all they are just numbers that you assign they're numbers that you assign to these state descriptions or states that are between 0 and 1 and they add up to 1. That's all a probability model is on this algebra. And so then I want you to consider the following constraint on this probability function. I'm calling it the equation. It was defended by Ernie Adams and Bob Stolacker in the 60s. And so what does this constraint say? It says that the probability of the conditional, now that's just an atomic sentence, remember, okay. The probability of the conditional is just the conditional probability of its consequent given its antecedent. That's called the equation. That was something that was proposed as I interpret it as a rational requirement on credence. Now, Lewis, in his 76 paper, assumes, and really without argument, and I'll talk about this later, it's puzzling, he assumes that if this equation is rationally required, that is, if it's an epistemic rational requirement on a credence function, that it satisfied this, then it should also be required that this constraint hold in a what I'll call a fully resilient fashion. And what does that mean? That means the following has to also hold if the first thing holds. I call it the resilient equation. So what does this say? This says for any x in this algebra, if you just think of the simple algebra, for any proposition x in the algebra that's definable in terms of P and Q, so any Boolean event x in the algebra generated by P and Q, provided that x is compatible with P, probabilistically, then the equation should continue to hold when you conditionalize on x. Okay, so if you put in a tautology for x, then you just get back to the equation. If you put in something more substantive, you get an additional constraint. And now, if you imagine doing that for all the propositions definable in terms of P and Q, you get what turns out to be an extremely strong constraint on the initial credence function here. How strong? Well, in a 2015 paper, I showed that it's stronger than anyone realized. It's very strong, stronger than anyone knew. So here's something that follows. I call it triviality. Provided that P and Q, that doesn't have probability 0, and the conjunction P and not Q doesn't have probability 0, then this conjunction has to have probability 1. The conjunction of P and this material biconditional connecting the consequent and the conditional. What that means is the antecedent of the conditional has to have probability 1. This is an arbitrary conditional here. Okay. The antecedent of the probability has to have probability 1, and the consequent has to have the same probability as the conditional. Now, I'll show you later exactly how strong this is. It takes you from 7 degrees of freedom to 1 degree of freedom. So it's not incoherent, but there's a very small set of probability functions that will satisfy this. Okay, so I showed that in 2015, and the way I showed it turns out to be important for what I'm going to propose later in a surprising way. I'll get to that in a bit. So Lewis, as I said, he assumed that any rational requirement on initial credence on a prior should be fully resilient, should hold no matter what you learn as long as it's compatible with certain things. And here's what he says. And I think it's supposed to be a defense of that, but it doesn't. It's totally a non sequitur. He says, the class of all those probability functions that represent possible systems of beliefs is closed under conditionalizing. Rational change of belief never can take one from a subjective probability function outside the class. And the change of belief that results from coming to know an item of evidence should take place by conditionalizing on what was learned. That's all fine and good, but it's not relevant. It doesn't entail that if a constraint holds, it has to hold resiliently. All that says, as I'll explain in a minute, is that if you start off probabilistic, then if you conditionalize, you still are probabilistic. Yeah, but that's just a theorem of probability calculus. So that's not an interesting thing about rationality. So if you think about things that are resilient, and there are some things that are resilient, the only one I know of that's uncontroversially resilient is probabilism itself, the claim that your degrees of belief should satisfy the probability calculus. That's resilient by a theorem of the probability calculus, which says if you start with a prior probability function, you conditionalize it, as long as it's well defined, you end up with a probability function. That's a theorem. So yeah, so probabilism is resilient. But substantive constraints that go beyond probabilism, like the equation or the principle, those aren't resilient. Okay. Okay, so basically this quote is just a truism. It's basically just talking about a theorem of the probability calculus. That's not relevant to what's at issue here, which is if you have a constraint, a substantive constraint that goes beyond probabilism on an initial credence function, that should hold resiliently. It should hold come what may no matter what you learn. That's the thing that he later rejects, and which I also reject because I just think it's just false. Okay, so here's my reconstruction of Lewis's argument, taken as a reductio of the claim that the equation is a rational requirement. Here's how, if you reconstruct the argument, here's how it goes. Suppose for reductio that the equation is a rational requirement on an initial credence function. Therefore, it must hold resiliently. That's the step that's wrong. Okay. So, therefore, the resilient equation must be a rational requirement. That just follows from 2. So, therefore, triviality should be a rational requirement, but triviality is not a rational requirement. It's this crazy strong thing that the antecedent has probability 1. So, therefore, contradiction. So, our initial assumption that the equation was a rational requirement must be false. Okay. Now, this argument, I think, is fine except for the first step. The first step is where it goes wrong. Why should it be that if a substantive constraint holds on pain of irrationality of an initial credence function, that it should continue to hold no matter what you learn? Interestingly, Lewis himself later rejects this assumption that 2 follows from 1. Okay, and that's what I'm going to exploit to reorient the discussion in this literature. Okay, so, sorry, let me back up. So, I'm going to move next to Lewis 1980, and here's what happens in the 1980 paper. He's not at all moved in that paper by an analogous reductio of the principle as a rational constraint on initial credence. In fact, he goes to great lengths to avoid the assumption that the principal must hold resiliently. And in fact, most of that paper is about how to do that. You got to talk about what admissibility is. Okay, so fast forward 4 years, and you get the paper on the principle. In that paper, Lewis argues, I think persuasively, that the principal is a rational requirement on initial creeds. Here's a kind of naive statement of it. The credence you should assign to P, conditional upon learning that the objective chance of P is equal to C, should be equal to C. If you learn the chance, then you should match your credence to the chance. Plausible principle, we pretty much use it all the time in real life. Like if you play games of chance, this is what you're doing. You're obeying the principle if you're playing rationally. Now, Lewis knows full well that if we require this constraint to hold resiliently, then we actually get something probabilistically incoherent. Consider the following resilientification of the principle. Just like we resilientified the equation, we could do that with the principle. We could say, not just that the credence you should assign to P should match the chance, if that's all you know, but it should still match the chance even if you learn X. For any X. That's crazy. That's just straight up insane. Here's why. It's incoherent. If you slap a universal quantifier on that, it's probabilistically incoherent. And it's very easy to see why. Take a case in which this thing is acting up on me. I'm not sure why. Maybe my batteries are, okay. Sorry, just let me back up. So take a case in which the chance of C is less than 1. The objective chance is less, so it's a fair point or something, okay. And assume that P is probabilistically compatible with that chance claim, so that the conjunction doesn't have probability 0. That's just to make the conditional probability in P sub X well defined. Now, suppose you learn P. Well, then the probability calculus says you've got to assign 1 in this case. If X is P, then the probability of P given P and some other stuff is of course 1 by the probability calculus, and not equal to the chance, which by assumption was less than 1. Contradiction. This is just probabilistically incoherent. This is worse than triviality, because this is a probabilistic incoherence. This is a violation of the probability calculus. Okay, Lewis looks at this and says, well, this isn't going to hold resiliently. But he does not, therefore, reject the principal as a rational requirement. And that's the key point. He maintains that it is, despite this. Okay. What does he do? He says, well, we're going to have to restrict the quantifier. So there's this little quantifier here, this one. We have to restrict it to what he calls admissible evidence. Evidence which is quote-unquote admissible with respect to chance information. That rules out a whole bunch of stuff, including P itself. But it rules out a lot more than just P. I'll get to that a little bit later, but it at least rules out P. So that's enough to show that this does not hold fully resiliently, and yet, despite that, still a rational requirement according to Lewis. Now, I think Lewis is right here. I think this is the correct. This permissive understanding of what it takes to be a rational requirement is correct, in my opinion. The original one was wrong. Now, let me just go through a few very puzzling differences between what happens with the resilient equation on the one hand and what I'm calling the resilient principle on the other. Okay. So, just to remind you, Lewis saddles Adams with the resilient equation, and that's how he tries to refute Adams' thesis. But rather than saddle himself with the resilient principle, which would be incoherent and crazy, he doesn't do that. He allows himself to a more permissive notion, and he restricts the quantifier. Okay, but now here are some interesting things about what's going on in these two papers. First, the resilient equation is not incoherent. It's merely trivial, as I'll show you in a minute. It's not incoherent at all. There's lots of probability functions that satisfy them, a lot fewer than satisfy the equation, but still plenty. It's not incoherent. Whereas the resilient principle is incoherent. And yet, he rejects the equation and not the principal. So that's already weird. This looks like better evidence against the principal than the analogous evidence against the equation. You see what I'm saying? Okay. It gets worse because When you look at this notion of admissibility in the 1980 paper, it's a mess. It's this weird metaphysical concept. It's not formally characterizable. There's all this stuff about oracles, and it's crazy. It's all this weird. I love that part of the paper, but it's not. There's no precise notion of admissibility to be had. There's no formal characterization of it. On the other hand, if I'm right, and now it's starting to look like I might be, if I'm right in what I present later, there is a purely formal way to characterize the requisite quantifier restriction on the Brazilian equation so as to avoid all trivialities. Not just that, it looks like it avoids all counterexamples. We'll talk about that later. This follows, so here's what I'm going to do in the how-to part. So in that paper I wrote in 2015, I not only showed that the result was stronger than everyone knew, I showed that that strongest result supervenes on two instances. You just need two propositions from the algebra to make it work. The denial of the consequent of the conditional and the material conditional connecting P and Q. Those two instances of the Brazilian equation are sufficient to give you the full strength of triviality. And so I thought to myself, well, now if I'm looking for a quantifier restriction, here's the dumbest thing you would do. Here's the thing that would first occur to you. The thing you would do, the most naive thing to do, would be to just look at this result I had, that the triviality supervenes on these two instances, and then say, here's how I'm going to restrict the quantifier. I'm going to rule out those two instances. It turns out that appears to work. It's just the simplest, most naive thing you would do. Sorry. And it appears to work. So that's going to be the strategy. I'm going to take this result I proved where I showed that the triviality results supervene on these two instances, and I'm going to say, well, let's treat the equation, Adam's thesis, the way we treated the principal. We're going to restrict the quantifier. We're going to talk about, if you will, admissible information relative to the indicative. And what are those things? Which are the admissible things? And here's the answer. Anything that doesn't fall into the supervenience basis for the triviality results. And it appears that works. Okay, so here's how you do it. So this is how you actually do it. I'm proposing this as a rational requirement, and I think it is, and I think it also anticipates not only avoiding the trivialities, but it avoids all the counterexamples that are in the literature too. So here's the constraint. I call it TE. All rational initial credence functions that satisfy the following restricted version of the Brazilian equation. For all factual propositions P and Q, and for all propositions X that are definable in a Boolean way from those, we should satisfy the Brazilian equation, right? This is just the equation now conditional on X, provided that X satisfies the following three constraints. The first one's just for definability. X has to be compatible with P, otherwise the conditional probability on the right is undefined. So that's just a thing you need for definedness. And then the other two come from the triviality results. You're not allowed to entail or confer a probability 1 on the falsity of the consequent, and you're not allowed to entail or even assign a probability 1 to the material conditional. Because if you do, then those are the things that lead to triviality, as my paper showed. So that's my proposal. So constraint 1 ensures that the conditional probabilities are well defined. Constraints 2 and 3 ensure that no Lewisian trivialities can be deduced. Because, as I showed in my paper, all the Lewisian trivialities supervene on those instances. Okay, this is pretty cool. So this shows you how you can treat the Adams thesis as a bona fide rational requirement on initial credence in a way that's free of Lewisian triviality. Okay, but there's a wrinkle, because there's another kind of triviality result that's out there that's a little bit different. So I'm going to explain how the setup already avoids that one too, but for a different reason. So Alan Hayek proves a different kind of triviality result. This is just a combinatorial result. And the way we've set this up also sidesteps that. Let me explain that. So what Al shows is that if you model the indicative conditional as a relation between propositions, then the equation has to fail just for combinatorial reasons. There aren't enough unconditional probabilities to match up with the conditional probabilities. It's just like a pigeonhole principle argument. Okay. And this is independent of Lewis's argument. This has nothing to do with the resilient equation. This is just the equation. Forget the resilient equation. This is an attack directly on the equation. Okay, so I got to explain how our setup avoids that, which it doesn't. So here's how it avoids that. Remember what I said in my initial setup. I said that what we're going to do is, for each pair of factual propositions, we're going to introduce a new atomic sentence. It's not a relation between events or propositions. It's not a relation. It's a new atomic sentence which, from the outside of the model, we're extra systematically interpreting as the indicative condition. What this allows us to do now is we're going to have enough unconditional probabilities, because we just introduced a new one. For every factual pair, we introduce a new atomic sentence. Notice this is not a factual claim, so there's no regress. For every factual pair, these are going to be huge algebras, obviously, now. But that's fine. I just want an epistemic model that gives the right answers about your attitudes towards objects of credence. I'm not doing semantics here. I'm doing epistemology. Okay. So the setup we already have, which instead of treating this as a relation, which can't work, as Hayek shows, we're just treating it as a new atomic sentence, which we extra systematically interpret as the indicative connecting the two factual claims. That now gives us enough unconditional probabilities to pair off with the conditional probabilities so we can satisfy the equation. Let me just point out one thing. There's nothing really weird about this. You might think, well, if you're a semanticist, you might think this is weird because when you're doing semantics, you want something more systematic, maybe even compositional or something like that. I'm not doing semantics. I'm showing how to do this, how to describe epistemological rational requirements. And for that, all I need are objects of credence. Okay. Now, this is not an unusual tactic. This is a normal thing. When we use probability models, like in confirmation theory and epistemology, it's very normal to introduce an atomic sentence which has some hidden logical structure that's not being systematically modeled. Let me give you an example. The paradox of the ravens. So, paradox of the ravens involves a universal claim like this: all ravens are black. And then we'll have an individual claim that some object's a raven, and then another claim that that object is black. And one thing we want to be able to say, so let's just call these X, Y, and Z, because they're just atomic sentences from the point of view of probability calculus, okay? What we want, we of course want this constraint to obtain. The probability of Z, given X and Y, should be 1. And we can do that. There's nothing prevents us from having an ordinary model in just probability calculus, which just has a sentential language. Nothing prevents us from extra systematically interpreting things so we can treat, say, quantified claims or claims with a different logical structure. That's just like what we're doing here. There's nothing new here. This was done in the 40s. You know, this kind of way of using probability models is not new. So it's not like I invented it for this purpose. That's just how you use probability models in epistemology. Okay. Now, let me tell you some other applications of this idea. Once you see this idea, once you realize, oh, this whole literature is based on this idea, then in order to be a rational requirement, you've got to hold resiliently. But that's wrong. So what if we rethink? There's a whole bunch of things that you have to rethink in the literature. I'll talk about a few of those, specifically just still in relation to the conditional, but there's other applications of this too, because there's other arguments in the literature that involve, if you will, resilientification of one form or another. So like Hannes-Leitgeb stability theory. That's a kind of resilientification. So there's lots of other applications, but I'm not going to talk about this. I'm just going to stick to the conditional. But I'll tell you some other applications of this basic move. So Richard Bradley wrote a paper, an analysis not too long ago, much more recent than the Lewis paper, in which he endorses or talks about something that he thinks should be a rational requirement for credence involving a conditional. And it's a principle called preservation. And what does it say? It says, provided that the antecedent of a conditional doesn't have probability 0, if the consequent has probability 0, then so should the conditional. And if the consequent has probability 1, then so should the conditional. Notice, this is just a constraint on unconditional probabilities. So it's much more like the equation than it is like the resilient equation. It just involves unconditional probabilities so far. Okay, now, his paper does some other things that I'm not going to talk about. What I want to talk about is what happens when you resilientify this. If you think, oh, if that's a rational requirement, then it's got to still be a rational requirement no matter what I learned. Well, then you get this, the resilient preservation principle. And all this does is it conditionalizes all the probability functions on X. and then quantifies. Like, that's how you resilientify. So this now says that an initial credence function should satisfy this constraint, which is just like preservation, except now I'm conditioning every occurrence of the probability function on x, and I'm saying it should hold for all x, provided that things remain defined, and x is Boolean definable and all that. Well, it turns out that resilient preservation is itself trivial. It's not as trivial as the resilient equation, and I'll show you in a minute exactly how it differs, but it's still pretty trivial. And so you could imagine running the same argument that Lewis ran against the equation against preservation. Here's how it goes. Suppose preservation is a rational requirement. Well, then it must hold resiliently. But then that's true. But that thing is trivial. So preservation is not a rational requirement. That's a terrible argument. That's what I'm saying. It's just a bad argument. Okay, so let me show you how these things relate to each other, just to give you put a little more meat on the bones. So here's our just case of a single P and Q and a conditional. Okay, so you get your 8 possible worlds, or classes of possible worlds, or 8 states, whatever you want to call them. And we can parameterize the probability function with 7 parameters, because this last one's just 1 minus the others. They have to add up to 1. Okay, the equation, not the resilient equation, just the original equation, what does it do? It reduces the number of degrees of freedom by 1, because it's basically just a single equation. And what it basically says is that this guy g now has to be this function of the other remaining variables. That's not trivial. I mean, it's a constraint, but it's not trivial. Okay. What happens when you look at the resilient equation? Okay, here's the resilient equation. That's trivial. It's almost everything's 0. There's 1 degree of freedom. You've gone from 7 degrees of freedom to 1. The only things that can get positive probability are these 2 states. And you'll notice those are the states in which P is true, and the biconditional connecting Q and the conditional are true. So that's just a visualization of the triviality theorem. Okay, and then what about resilient preservation? Well, you'll notice it's still pretty trivial. You have 4 zeros. You don't have this many zeros. You don't have 6 zeros. You have 4. And you can see that this is just weaker than this. This entails this, but this is weaker. But it's still trivial. I mean, having those zeros, that doesn't seem like a rational requirement. And I agree with that. But that's no reason to reject preservation. What it's a reason to reject is the assumption that if something's a rational requirement, then it has to hold resiliently. Okay, so this is just to give you the details of those technical results. That's what they are. That's basically the sum total of those results and those constraints and what they really mean algebraically. Okay, so the equation just reduces the number of degrees of freedom by 1. That's not trivial. It's a constraint, but it's not trivial. Resilient preservation reduces it by 4, and then the resilient equation reduces the number of degrees of freedom by 6. And now you're down to a very slim set of probability functions that will satisfy the resilient equation. Okay. I take this to just show that resilientification is a bad idea. That's not something you should be just allowed to do to a rational requirement. That's what I think it shows. It doesn't show the equation should be rejected. It doesn't show the preservation should be rejected. Just like we did with the equation, we can give a triviality-free way of modeling preservation as a rational requirement on an initial credence function. And here's how it goes. I'll call it P. All rational initial credence functions should satisfy the following restricted version of resilient preservation. For all factional P and Q and for all X definable in terms of P and Q, resilient preservation should hold, provided that X satisfies the following 3 constraints. First, it can't have probability 0 because then none of the conditional probabilities, otherwise none of the conditional probabilities would be defined here. Secondly, it can't confer probability 1 on not Q. That was also a constraint for the equation, if you remember. And it can't confer a probability 1 on Q either. Constraint 1 ensures that everything's well defined. Constraints 2 and 3 ensure that no Lewis-style trivialities can be introduced because it can be shown that the Bradley trivialities for resilient preservation supervene on 2 instances, Q and not Q. So this is the same strategy now applied to preservation instead of the equation. And my conjecture is this is a rational requirement, just like Bradley wanted. This I think will be the last application. Ruben Stern and Stephen Hartman and I have proved a new impossibility result, not just a triviality result, an impossibility result for the indicative conditional. And it rests just on 2 assumptions. It starts from 2 assumptions. So here's the constraint I'll call MPI. And it says that an initial credence function should satisfy the following two conditions. The first one is just modus ponens. The probability that the consequent is true, given the conjunction of the antecedent and the conditional, should be 1. Remember, P and Q are factual here, so no one thinks there's counterexamples to that. Everyone accepts that. These are factual P and Q. The only counterexamples involve non-factual content. So that's fine. And then, what we call independence, and that says that the conditional should be probabilistically independent of its antecedent. Now, modus ponens is just true. There's no counterexamples to that. Independence is something that has been defended by various people, especially in the presence of the equation. In particular, Daniel Rothschild defends it in a not too old paper. And so we thought, okay, great, let's put those together. Someone like Rothschild would defend those. But now you think, well, wait, what if we resilientify MPI? What would that look like? Well, if you resilientify it, the first condition doesn't matter, because since that's already an extremal probability, adding an x here won't change anything. Once Q has probability 1 given this stuff, it'll still have probability 1 if you can join another thing, but that doesn't matter. This is the one that gets affected, independence, right? So if you resilientify independence, then you say, the conditional should be independent of P of its antecedent, given anything you might learn. It should remain independent no matter what you learn, as long as it's compatible with things that are relevant. That is probabilistically incoherent. So we have a theorem in our paper that shows that there are no probability functions that satisfy resilient MPI. None. It's not just trivial, it's incoherent. So this is more like the principal case. So here's what we propose. The same thing. Here's what we propose as a restriction on the quantifier in resilient MPI. We say all initial credence functions satisfy the following restricted version of resilient MPI. For all factional P and Q and for all x definable in terms of P and Q, you should satisfy resilient MPI, provided that x satisfies the following two constraints. First, you don't get probability 0 when you conjoin it with the ingredients of modus ponens, the premises of the modus ponens. All that big conjunction still has non-zero probability. That's to make the conditional probability in MP well defined. And here's a disjunctive condition. Either x doesn't confer probability 1 on Q, or it doesn't confer probability on not Q. Why? Because if it confers probability 1 on both, that's what drives the incoherence. In other words, if Q screens off P from the conditional, then that's incompatible with modus ponens. That's what we proved. So just don't do that. Those are inadmissible x's. So don't do that. And we think what you get then is a rational requirement. Condition 1 ensures the conditional probabilities are well defined. And constraints 2 and 3 ensure that no incoherence can be deduced because the incoherence supervenes on those instances, Q and not Q. Okay. All right. Now, that's the end of the main part of my talk. Do I still have a little bit of time? Do I still have 5 more minutes? Can I do? So here's how this thing went, and then I'll tell you what's been happening recently, which is more empirical evidence in favor of these conjectures. So, like I said, I read the papers and I thought, oh, wait, the 1976 notion of rational requirement is just too strong. The only thing that satisfies that is probabilism. So why would you think that a substantive constraint like the equation, or the principal, or any of these things would be resiliently true? So then I thought, okay, well, if they're not, then we need a quantifier restriction. So I thought, well, what's the simplest quantifier restriction that comes out of the triviality results I proved? And I thought, well, you just take the instances that generate the triviality result and rule those out and say you can't learn those. I mean, I don't have an explanation for this. I'm just saying this is what I did. Now you think, well, that's miraculous. Why would that work? I don't know. I don't have an answer to that. But here's what's really interesting. I've been asking around people who work in linguistics and philosophy of language about the addictive conditional. I've been asking them for counterexamples to the resilient equation. And I've learned there are many. Let me give you one. This is due to Paolo Santorio, who's been very helpful for me on working on this paper. So, a fair die has been tossed, and I want you to consider 3 propositions. P, the die landed either 1, 3, 5, or 6. Q, it landed 6. X, it landed even. And I want you to notice, as you think about this, you can, a little bit, you'll notice that X is the material conditional, P hook Q. And that's not, I don't think it's a coincidence. That's what's weird about what's happening in this literature right now. Okay, well, I'll come back to that. So now, let's just look at what happens. Well, we have a very well-defined probability model from the principle, and it looks like this. Okay, so you got P and Q, so now I'm just looking at the model over P and Q. Well, what's the probability that P and Q are both true? Well, that's just the probability that it landed on 6, because Q entails P. So it's 1/6. What's the probability P is true and Q is false? Well, then you've got 3 possibilities left out of 6, so that's a half. What's the probability that Q is true and P is false? 0, because Q entails P. What's the probability they're both false? Well, a third. Okay, because that's just the probability that P is false. Okay, now, so that's uncontroversial. That's just the principle. And now you can start to calculate probabilities. Okay, so here's the first thing to notice. The equation, not the Resilient equation, just the equation, tells us what the probability of the conditional has to be. It has to be a fourth, because it has to be the probability of Q given P, and that's determined by this Q 1/4. That's just determined by the principle. It's just a ratio of unconditional probabilities, which comes out to a fourth. Okay, now, what that means is, if you ask what's the probability of X and that, it has to be less than or equal to a fourth, just by the probability calculus. It's a conjunction. It's stronger. So it can't have a greater probability. Its probability has to be less or equal to a fourth. Okay, but now we can reason as follows. The probability of the conditional given X is just the probability of the conjunction divided by the probability of X. That's just the definition of conditional probability. Oh, but we already know that the denominator is 1/2, and the numerator is no greater than a fourth. So the ratio is less than or equal to a half, which is way less than 1. Counterexample to the Resilient equation. Because X just is the material conditional. And so that probability has to be 1 by the probability calculus. Counterexample. Wow, okay, so the Resilient equation is false. I'm not surprised. That's kind of the whole point of my paper. Of course it's false. It's a ridiculous thing to Resilientify something like that. But it's not a counterexample to my principle because it involves exactly one of the cases that leads to triviality, the material conditional, and so violates my constraint, my admissibility constraint. Now, here's what's really interesting about this literature. I've been asking people for examples. Every compelling example that I know of either involves learning that the consequence is false or learning something that entails the consequence false, or involves learning the material conditional or something that entails the material conditional. I have no explanation for this, but it's just confirmation that my conjecture is true, and that in fact, when you apply the correct notion of rational requirement to Adams' work, you do get a rational requirement for initial credence. Thanks.